Welcome to this video on sampling distribution of a difference between two proportions. By the end of this video, you should be able to calculate the mean and standard deviation of a sampling distribution of a difference between sample proportions, and if appropriate, use the normal calculation to determine the probabilities involving the difference between two proportions. Alright, so our scenario is we have two teachers, Mr. Wilcox and myself, who believe that so Mr. Wilcox believes that Skittles have a higher proportion of orange candies than M&Ms, while I believe the opposite. Who is correct? So I took a sample for us. So for our Skittles, I got a sample of 13 oranges out of the 50. So I got a sample proportion of 0.26. Okay. And then for the M&Ms, I got 9 oranges out of 50 for a sample proportion of 0.18. And so to find the difference, we're just going to subtract. We got 0.26 minus 0.18, which equals 0.08. So before we go any further, I want to give us some symbology to make sure that we're using. This is a sample, so it's a statistic. This came from so it's the proportion of oranges in my Skittles. So I'm going to say p hat of s equals 0.26. And so this sample statistic came from the M&Ms, and it's a proportion. So I'm going to say proportion of M&Ms equals 0.18. And this is the p hat of s minus the p hat of m is going to equal the 0.08. Alright, so I ran a simulation for us, and I got a sampling distribution. So I'm going to give you my results here. So here's the sampling distribution I got. If you need to, pause the video so you can copy this down. But remember, each point on our sampling distribution represents the difference between one sample of Skittles, the proportion of orange, and the proportion of orange in one sample of M&Ms. And it is a sampling distribution. And we got it by doing this math. So we're going to label it that. So pause the video if you need to get that. What does each dot represent? It represents the difference in proportion of orange candies for one sample of 50 Skittles and one sample of 50 M&Ms. Alright, so for our dot plot, for the shape, when I look at it, it might be a little bit skewed. But I'm thinking it's really approximately normal, and here's why. The center of it, I actually think, is right in here somewhere based on the dots. If I'm just looking at the dots, I feel like the center's here. Okay, so I'm going to say the shape is approximately normal. Of course, we never want to say that it is normal. So I'm going to say that the shape is approximately normal. And the center, I think, is kind of like right in here. I'm not for sure, so I'm going to say, so it's somewhere from 0 to 0.2, somewhere in there. Now the variability, that's your standard deviation. I'm making a guess here, and I was kind of estimating if I think the center is here, and I'm thinking of my empirical rule of the percentage of data, I estimated it to be about 0.06. Okay, and so that's just me guessing off the top of my head using some knowledge of the empirical rule. Alright, so let's go ahead and flip this over and continue. So I did a Google search on orange candies for Skittles and M&Ms and found that 21.6% of Skittles are orange and 20% of M&Ms are orange. So we're going to fill out this chart with some information. There's some conditions that we're going to need to check. So first we're going to talk about the samples individually. So we're going to look at the one sample first. So I have two different one samples. okay, for Skittles and for M&Ms. To talk about shape, whenever you're talking about shape, that's your large counts. Our mean, remember the mean of the sampling distribution is the same as the population proportion. And then your standard deviation is going to be the square root of success times failure divided by the sample size. These are formulas that we've talked about before. So for our Skittles, large counts you want to check, N times P, so 50 times 0.216, because the Skittles, the population has 21.6%. So we're going to say 0.216 equals 10.8, which is greater than or equal to 10. So we're okay there. All right, and we're going to do 50 times 1 minus P, which is 0.784. And I got 39.2 there, which is also greater than or equal to 10. And what that means is because they're both at least 10, it means the shape is approximately normal. So for our mean is the mean of the sampling distribution will be the same as the population proportion, and our population proportion is 0.216. Okay, and now the standard deviation. The standard deviation of our sampling distribution for Skittles will be success times failure divided by sample size. And I got 0.0582. Alright, what I'd like you to do is stop the video and go ahead and try this column on your own. Okay, so when I checked my large counts, both were at least 10. This one is 10, but that's greater than or equal to 10, so we're okay there. So we were approximately normal. The mean of the sampling distribution for M&Ms is 0.2. And remember that 0.2 came from right up here. Okay. Our standard deviation, I got 0.0565 when I plugged in all of my values. Now, that's one sample when we look at them individually. Now, when we put them together, it becomes a two-sample issue, because we're putting them together in the same problem. So when I look at, for shape, these were both approximately normal. So I'm going to say that the shape is also approximately normal. The mean difference in proportions, and we were told Skittles minus M&Ms. It says X minus Y, and they put them in this order. So that's X minus Y. So Skittles minus M&Ms. Okay. So I'm going to use that symbology. Skittles minus M&Ms equals 0.216 minus 0.2, and I got a difference of 0.016. All right, and then the standard deviation. Now the standard deviation, you have to remember back to when we were transforming our data. We could add and subtract to the mean when we were combining our distributions, but when we combined our distributions, it didn't matter if we were adding or subtracting, we always added for our standard deviation, and we had to add the variances. So here's our standard deviation. So to get back to the variance, you've got to square that number. So 0.582 is the standard deviation, 0.852 squared is the variance. Okay? And then plus 0.0565 squared. So I got a standard deviation of 0.0811. Okay. Now we're going to do some normal calculations. The whole point of this right here is that it's normal, so we can use a z-score. So I want to find a z-score. So that means I'm going to have to do some drawing here. So I have a normal curve. My mean is 0.016, so I'm going to label it normal 0.016 with a standard deviation of 0.0811. Okay, and so on the front we had a proportion difference of 0.08. I want to know how unusual is that. 0.08 is right here, and or higher because it's or more extreme from the mean. Okay, and since we're on the right, we're going to go up. So my z-score is the score of interest minus the mean divided by the standard deviation. And when I did that, I got a z-score of 0.79, meaning 0.79 standard deviations above the mean. When I look up the area on table A, I got an area of 0.7852, but that's really this area because the table always gives us the lower, so to get the upper I do 1 minus. I got an area of 0.2148. So there's about a 21.5% chance of getting a difference of 0.08 or more extreme, so not unusual at all. So our difference was not that unusual. All right, so I don't really have any evidence to suggest that Skittles have a higher proportion of orange than M&Ms. So really we don't have any information that helps us settle this right now. All right, so let me give you what the formulas look like. So when we have two samples together, you have to check for your large counts. You have to check all four of the conditions. N times P, the first sample, and N times 1 minus P for the first sample have to both be greater than or equal to 10. And you do the same thing for the second sample. So it's really combining these two that we did up here together. Greater than or equal to 10. All four of those have to be true for this to be considered approximately normal. Okay. So our mean we did just fine there. So for our standard deviation, you're going to take success times failure for the first sample divided by the sample size of the first sample, plus you're going to do it for the second sample also. Okay, and we can see if we look at our formula sheet for a sampling distribution of proportions, which is what we're talking about. It's broken down from 1 sample to 2 sample, and you have your formulas here to look at, so you're not having to worry about memorizing these. They are on your formula sheet. Okay. Then the last part, this looks really crazy. This was our z-score. We got 0.08 by taking our sample proportions and subtracting them. And then we subtracted the mean, which was our population proportions subtracted. And then we got our standard deviation by this big long standard deviation. Okay, so it looks big and crazy, but it's the same thing that we've been doing all along. It's just telling you where the numbers actually came from. So let's flip this over and make sure you get your takeaways. All right, there are two major topics I want to be sure that you take away from today. So when we're talking about the sampling distribution, the difference in proportions, to find your shape, we're really looking to see if it's approximately normal. That's what we're checking so we can do these normal calculations over here. So it's going to be approximately normal if you check those four conditions of these being greater than or equal to 10. All four must be true for this to work. All right, for your center, you just find your center by subtracting. So your sample will be the same as your population. Remember, that's that unbiased estimator that we talked about before. And our last is our variability, which we usually are talking about standard deviation here. And you're adding there even if you might be subtracting and looking for the difference of proportions. Okay, so those are those formulas summarized for you. When you do your normal calculations, you need to be sure to include a drawing, and the drawing needs to have the mean, which you got for taking the proportions and subtracting them. You need to label the score of interest, whatever it is. That's your p-hats when you subtract them. And you need to do the shading that's appropriate depending on where you're labeling. You also need to have the n with the mean. And the standard deviation. Okay. Once you've drawn it, you can run your z-score. And find the appropriate area. All right. Once you're done, go ahead and do the Check Your Understanding. Upload it to the link in Canvas. Let me know if you have any questions. Hopefully I'll see you in class again soon.